Hi, I'm Mark Perry. Welcome back to Colorado Dam Safety's video tutorial series on our new guidelines for hydrological modeling and flood analysis. This video covers Section 7, HEC HMS model setup. So this is the cover sheet of our new guidelines for hydrological modeling and flood analysis. The current final version is dated September 12th, 2022. And those are official. They're on our Division of Water Resources Dam Safety webpage. The guidelines are living documents, so they may be updated. You may see updates issued with a later date, but as of September 12th, 2022, these guidelines are final. Take a quick look at the table of contents and just review where we've been and where we're at. So through the video series, we had a initial video that talked about these two top flow charts and explained the difference in our new processes between risk evaluation of existing dams versus inflow design flood studies for designing for design projects for new dams, enlargements, or modifications of existing dams. All right, then we went through the introduction and background of these new hydrology guidelines, an overview of our new modeling methods, and then into creating the input data, getting the basin properties, and then doing all the parameter estimation. So that was section 6 that we just finished was parameter estimation. At this point, we have all the model parameters, and we're going to go into HMS in this tutorial and set up the model. So, which is pretty easy at this point since all the parameters have been estimated. All right, so the overview of this video is that we're going to go through the HMS model creation, and that was actually covered back in section 5.2. I'll recap that, but then we're going to go through the rest of the model. The new model setup now, or the rest of the model setup, includes the precipitation gauges setup, the meteorological model, basin model setup, creating the control specs, and then QC checking the model. As I said, at this point in our process, if you're following through the guidelines, linearly, you will have already estimated all the model parameters. So it's a fairly easy setup at this point of just inputting that into HMS. In section 4, we estimated created all the input, and that included creating the reps design storms with PMP and precipitation frequency. So that's a major part of the inputting the forcing rainfall into the HMS model. And then in section 6, we did section 5, we estimated the basin properties, and then those properties were used in our ARC toolbox, the CSU SMA Python script, to estimate parameters for the rainfall loss method, and then we had a spreadsheet for estimating parameters for the Clark unit hydrograph, and then parameters for rerouting by the Muskingum-Kunch method. So we have all those parameters estimated. The input that we need out of this process thus far in order to set up the model is just the reps design storm. So there's PMP and precip frequency temporal distribution output. Those are in way of text files and CSV files. And then if you're doing partial area analysis, we talked about that pretty thoroughly in the section 4 tutorial and section 4 of the guidelines. But if your basin area exceeds the storm area size limits for the different rep storm types, then you would do partial area. And anyway, to set up the model, we're going to want to know the partial areas that should be used with each storm type. And lastly, table 6 is kind of that summary parameters, or it is that summary parameters table. It's useful to have that and just work off that. I think it's useful to work off that to set up your HMS model with all your summary list of all your sub-basin model parameters. Okay, let's flip to the guidelines. Again, section 7 here, HMS, HEC HMS model setup. There's a lot of qualifiers. It could say a lot of them, we've already said in previous tutorials. Of course, you can use different models, different rainfall runoff models. I think the vast majority of people are going to be using HEC HMS, so that's the way we have written these guidelines. And if you're using some other model, then I guess the burden would be on the engineer to figure that out. But I think we covered in section 3 the model overview and tried to make it general enough that the same principles and methods could be applied in other models. So anyway, we're talking about HMS. We've also made the disclaimer that everyone who uses HMS knows the versions change a lot. Currently, we're using HMS version 4.10, and the original CSU Colorado State University hydrology research study that our methods based on was done using HMS 4.7. We have not seen any major changes that would affect the method at this point. But we're currently, as of this video, we're using HMS 4.10. Okay, so as far as setting up the model, we already created the model in section 5.2. So if you go back to the tutorial video in section 5, or section 5 of the guidelines, it walks through importing your DEM, importing the DEM as a terrain through the terrain manager in HMS, and then creating a basin model and linking that terrain to the basin. Let me just go ahead and bring over HMS here so we can show what we're talking about. So we had the terrain, then we created the basin model and linked the basin model to the terrain, and then we went through all of the GIS processes for HMS to create a stream network. So that involved, under GIS. So it asked us to create, the coordinate system when we linked the basin with the terrain, and then we processed sinks, which, as the guidelines explain, that's at the discretion of the engineer if those sinks should be processed. But anyway, we processed sinks and the drainage. It identified the stream network. We put in a breakpoint at the outlet. In this case, you could put in other breakpoints where you want to create specific sub-basins or at calibration points, say if there's a stream gauge in or some paleo flood estimate or indirect flood estimate that you're calibrating to in the middle of your basin, you could create a sub-basin there. And then we delineated elements. Okay, and then after we had the sub-basin and the basin structure created in HMS, then we exported that through the GIS. And the reason we did that upfront in section 5.2 is because we were using the terrain in HMS to get all the sub-basin properties for us. We used this parameters tab, sub-basin areas, characteristics, sub-basin characteristics, and reach characteristics. We used the sub-basin characteristics output in our Clark unit hydrograph spreadsheet to create the Clark unit at least our initial Clark unit hydrograph parameters. We're going to calibrate those later on, but for now that was our starting point, and then our reach characteristics that we used get our parameters for the Muskingum reach routing. And then we exported the sub-basin shapefile, and that's what we used in our CSU SMA Python script, our toolbox, and we ran that sub-basin shapefile through to generate all the model parameters for the rainfall loss method, which is the HMS soil moisture accounting loss method. Okay, so after that in section 5.2, we had the terrain. The model we let the model create the sub-basin and the the stream structure, and so HMS automatically created this all the elements, the structure of the subbasin model, which is pretty cool. But there's nothing in these, so they're just default methods, and there are no parameters in them yet. So here's subbasin 1 up here, but there's just default method, element default methods there, and no parameters inside of those if we can. So yeah, there's no parameters filled in there. Okay, so one thing that I did not do here that's a helpful tip, just a pro tip, is I could set the if you're doing a lot of modeling for our method, you can set the methods in HMS under the default. So tools and program settings, and then you can go to defaults and say for our case, I did not do this because, as I mentioned, HMS changes all the time. I just started using 4.10, and I had not gone through and set these in 4.10 yet, but I will. And then we can just use the simple canopy method. We can use the loss method is soil moisture accounting. Okay, here, and then we're using Clark unit hydrograph, linear reservoir for base flow, reach routing. We're using Luskingham-Kunge. There's no reach gain or loss. Precipitation, we are using specified hydrographs, and that we have nothing on temperature, evaporation, and snowmelt. And I guess it's important here up top we had U.S. customer units there, and element sorting, however you prefer to do that. But anyway, that's probably a helpful tip if you're doing a lot of modeling for our methods, and just set those defaults up front. So when you go in section 5, create the basin structure, then at least all the methods will be correctly in each element. So as I said, I did not do this, so I'm going to have to set them as I go here. All right, but before we do that, before we go through and set up the actual subbasin methods and parameters, we're going to first deal with the rainfall, and that's going to be done first by creating precipitation gauges, and then secondly, we're going to create meteorological models under the components, and we're going to set those to the specified we're going to create evaporation and link the MET models to the specified hydrographs for each reps design storm. Okay. This is a fairly big effort, and there's just probably no way around it except to put on some good music and to create these precipitation gauges. We'll try to give you a few little tricks, and you might have more of your own. But it's just a bit of a process to create all these, because there are potentially, depending on your basin location, there are potentially up to 26 reps design storms. Okay, so there are 3 storm types and precipitation frequency, 7 different AEPs. So that's 21 precipitation frequency or probabilistic design storms. Then there are the PMP storms. There's a local storm, 2-hour storm, a 6-hour storm, and if you're on the Front Range below 7,500 feet, Eastern Plains, Front Range foothills, there's a 24-hour local storm. There's always a 72-hour general storm, and then if your basin lies south of 38.5 degrees latitude, then there's also a tropical 72-hour tropical storm. Okay, so if you total those up to 27 storms, where we're creating a precipitation gauge and then a MET model linking to each of those. Okay, so let's jump back to the guidelines and talk about some of the parameters on those. First, we have to set a time interval, and what we use is we just use the time intervals that came out of the REP study. Okay, so for PMP local storms, the PMP local storms were developed on a 5-minute time interval. So that's the 2-hour PMP local storm, 6-hour PMP local storm, and 24-hour. They all have a 5-minute time interval coming out of the REPS PMP tool, the ArcGIS tool. Okay, the REPS PMP 72-hour storms, the general storm and the tropical storm, were developed with a 15-minute time interval. So we just say to keep those, just use those in HEC HMS. I mean, that's the easiest thing to do because we're just cutting and pasting from the REPS tools into HMS. Now, the precip frequency, different product, different part of that REPS contract, but it was developed with different time intervals. The local storm precip frequency, that's the 2-hour key duration local storm, was developed with 5-minute duration. The MEC, mesoscale storm with embedded convection, the 6-hour key duration storms, precip frequency, were also developed with 5-minute duration, but then the REPS precip MLC, the 48-hour key duration mid-latitude cyclone storms, precip frequency, were developed with a time interval of 1 hour. So we say just to keep those. All right, and then we have to specify the duration in HMS under our each of our precip gauges, and we give the following general guidance on the storm durations, which also is going to be our control spec or our model simulation duration. But for the local storm, 2-hour, 6-hour, 24-hour PMP local storms, and for the two smaller precip frequency storms, the 2-hour local storm and 6-hour MEC storm, we say to use a 2-day duration. Okay, so that's 2,880 minutes. The reason being is because those storms are high intensity. They are mainly surface runoff or near surface, shallow subsurface, surface, quick flow, and they happen relatively quickly. So 2 days, even for a 24-hour storm, 2 days seems to be enough for all that water to run off. Now, for the longer duration storms, 72-hour PMP, the general storm, tropical storm, and then the 48-hour MLC precip frequency storm, we say to run those out 10 days. Reason being is because our method uses the soil moisture accounting and then the groundwater layer with return flow through the linear reservoir. So as you start to get these low intensity, high volume storms, you start to see a lot of groundwater. That groundwater, if you remember from the previous sections, we're estimating those parameters. Those have long time, the groundwater has long time lag coefficients. So you can be talking several days for that groundwater component, subsurface component, to reach the streams and to flow out of your basin. And so we want to see that complete hydrograph in a volume case, where volume may be controlling. So we just, as a general guideline, say to run it out 10 days. The more specific or overarching guide is that at the end of your simulation here, this note under Table 9 in the guidelines, at the end of the simulation, discharge should be equal to less than 5% of the peak flow. So your hydrograph should pretty much have returned. The recession should be returned to your base flow or to zero within 5% of the peak by the end of your simulation duration. Okay, anyway, this is the duration that your storms have to be created for. So we have rainfall data for the entire storm. Okay, and then we can just copy and paste. The idea is to copy and paste the temporal distribution output from the REPS tools into HEC HMS. So the REPS tools don't give these durations. They stop at more like the durations that the inner durations are for. So the 2-hour or 6 hours or 24-hour storm, okay, not necessarily a 2-day or 10-day. So all we did here is just created a very simple spreadsheet that just that just extends the data to the recommended simulation time series duration. So the 2 days, 10 days durations for the respective storm type. So if we click on that hyperlink, it'll take you to our Google Drive, and you're certainly welcome to download this spreadsheet. It's an Excel, pops up in Google Sheets inside of Google Drive, but it can be downloaded as an XLS spreadsheet, and then you can copy and paste your reps temporal distributions into these, and this spreadsheet extends them for you for the right durations. And then in order to then be able to just copy and paste them and put them into HEC HMS as precipitation gauges. All right, I'm not going to download this right now. I already have. So let me just take you to the XLS spreadsheet that I've downloaded here. And this is pretty self-explanatory, but I want to go ahead and just run through at least one case of this. So, all right. So let's say here we have starting with the precip frequency storm, 2-hour local storm. So I'm going to go to where I have all my reps output, and my input, the way I'd organized it, if you recall, was the kind of the way the guidelines are set up is input data, parameters. And so under my input data, I have the reps output, so 2-hour local storms, and then there's a temporal distributions file, and that's a CSV file. It opens in Excel, and I just converted it. I just opened it in Excel, and what I did is I just deleted it. The reps met portal output gives columns for incremental and cumulative or accumulated rainfall by AEP, and all I did was just delete the incremental, because we're only using cumulative here. So that's generally, we recognize that as a personal preference, incremental versus cumulative, but I tend to use cumulative rainfall. It might just be nice for consistency, but certainly neither one of them is wrong, just different. So now what I would do here to get this extended, if you can see, this is a 2-hour local storm out of the reps met portal precip frequency, and the tool gives you download all of the AEP temporal distribution. So it's the unscaled pattern, then scaled by the AEP precip frequency estimate for each key duration. So here for 2 hours. I think we went over that in section 4, hopefully pretty well, but if I could just show it really quick, if I can, going into Met Portal, and you would load your basin shape file, go to the watershed precip frequency estimate, and get your precip frequency table and curve, and then you would go to temporal patterns. You would pick the storm type. So in here we're doing the 2-hour. You would pick your, I think I have to upload the shape file first, which I'm not going to do right now, but, or heck, I can just go ahead and do it so I can show you. Let's just do one here. Okay, we can find something pretty easily, hopefully. Okay, so we just pick a basin file. And if you remember in Met Portal, I don't want to get sidetracked on here in Met Portal, but if you remember in Met Portal, we do not want the subbasins. We just want an overall base, because it does not do subbasin analysis. And I think having subbasin elements in the shape file confuses it. It's recommended to just use the overall basin shape file here. Okay, and so there you can see what I imported there is the basin shape file. And this happened to the one I just grabbed was for Jimmy Camp Creek, east of Colorado Springs, and outletting Fountain, Colorado, there on the plains, frontage, foothills. Okay, if I go back to the temporal patterns tab then in Met Portal, I picked the 2-hour local storm key duration, and now it's letting me select a storm type. Okay, so I want the synthetic storm, and our reps guidelines. We have a separate reps guidelines document. They talk about all this, and they tell you what storm type to temporal pattern, the unscaled pattern to use for each design storm. So for the 2-hour local storm, precip frequency in Met Portal, it's this synthetic storm. And there's also vary by region. So we're in this eastern macro region. It's the synthetic storm. Okay. Point being here, okay, that was a little bit of a diversion. Let's get back on track here. Point being is if I check this box, I download the data for all AEPs. So then when I download this data, I think I have to pick a storm to scale it to. Yeah, it's asking for a storm to scale the graph to. So I just picked 1 to 100 as just a default. But it's going, when I check this box and then I download this data, it's in the spreadsheet that it gives me. It's going to give me the scaled pattern for all of the AEP storms, 10 to the minus 1, 1 in 10, through 10 to the minus 7, 1 in 10 million. Okay, so that's in this file that we downloaded. When we pop that open, all the local storm scaled temporal distributions are in here. And these are long headings, but it's 10-year here out through 10 million, as you can see. And as I told you, it comes out with one column for incremental and one column for accumulated. I typically just go through and delete the incremental ones because I'm only interested in cutting and pasting the accumulated patterns. Okay, so that was a bit of a side tour through Met Portal, but hopefully that would just clarify that for anybody who needed that. All right, so I took the temporal patterns out of Met Portal. Once I eliminated those incremental distributions, I took these scaled accumulated patterns. This is for the 2-hour local storm. It has 120 minutes is the key duration, but the distribution extends out of Met Portal to 240 minutes. Okay, so I copy that. I just go over to this little spreadsheet tool that we created to extend the distributions. What I'm doing is overwriting this blue text, and the spreadsheet explains that in the top. Overwrite the blue text. I do a paste, just numbers, and it fills in this table. There's a highlight here that just tells you this is the key duration. You can cross-check this key duration line against your precip frequency table or the estimates and just make sure that you've got the right distributions in there. It's just a nice double check. So your 10 to the minus first estimate here should be 1.15, 10 to the minus 2 should be 1.94, etc. And then going down, that filled in the table through the reps Met Portal duration of 240 minutes, but we need to go down to 2,880 minutes to extend our precip gauge in HMS out to 2 days, right? So all the spreadsheet does, it's very simple. What all it does is just copy this last line, and it just automatically runs it down for you to 2,880 minutes. In this case, because for 2 hours, we're recommending you run the model for a 2-day duration. Okay, so there it is. All right, so that's all that spreadsheet does. Let's get rid of that for the moment and go back to get rid of our Met Portal output. All right, and then let's go back to, that was here in the guidelines where we linked to that spreadsheet that extends the reps temporal distributions. Okay, and then let's get ready to go back to HMS. There is another pro tip here. And I'll go ahead and read this since we're in the guidelines, and then we'll talk about it here and we go to HMS. A pro tip is that we could since there's a kind of a set number of um, time interval and duration combinations here, what we can do is just create a kind of a dummy precip gauge that would have, say, for example, 5-minute time interval, cumulative inches, and 2-day duration. And then we could just use that as kind of as a template in HMS. Just copy that precip gauge over for the 7 AEPs, and then for all the storms that use that 5-minute, 2-day time interval, and duration combination. So it's the local storm, the MEC, and then the reps for precip frequency, and then for PMP 2 hour, 6 hour, and 24 hours. So that's a whole bunch of storms. You can just copy over, and then all you have to do is cut and paste the temporal distribution numbers from the spreadsheet, our time extension spreadsheet, directly into HMS, and you're done. So it's just maybe a little bit of a time saver. Okay, figures 9 and 10 show the setup of those precip gauges, but we're going to do better than that in the video. We're just going to go to HMS itself and take a look at the precip gauges. Okay, so let's go through creating these precip gauges for the design storms. I've created a couple here already, so just show you. We'll just kind of walk through it step by step. But I created a 2 hour local storm, 10 to the minus 1. Let's rename that 10 to the minus 1 AEP storm, and then that has a 5-minute time interval. As we said, we're using cumulative inches, manual entry, and then I'm not. These are design storms, so I'm not concerned about any particular date. Just the default's January 1st, 2000. So the thing is just the duration, and so we want a 2-day duration here to the 3rd, 00 hours, and that gives us a blank table. I'm working off of our spreadsheet from Excel that does the time extension to our local storm. So I just copied all of this, and I'll do this again, but copied all of this data down to the 2880 2-day, 2880 minutes, or 2-day duration, and pasted this copied that and pasted it into HMS, and then you can see that has the cumulative rainfall graph for the 2 hour. That's the 1 in 10 or 10-year AEP storm, local 2 hour local storm, about 1.2 inches of rainfall in about 2 hours, and then it just extends that rainfall hydragraph out to 2 days to allow 2-day simulation. Okay, so then what I was saying is then we could, and again I'm going to rename this. I'm going to call these 10 to the minus 2. Okay. So what I was saying next is that we can just copy, once I have a precip gauge set up for this 5-minute time interval and 2 hour 2 hour duration set up, and I could just copy these over for all the storms that use that specific interval and time duration combination. So that's what I did here. Just copied a one and named it 10 to the minus 2, and then if you see, that one is still has the 10 to the minus 1st rainfall in it, or I could copy it before I paste that into it, just leave them blank. But I'm just going to go ahead and create a bunch of copies of those, and so I'm going to call this, do a 10 to the minus 3rd storm. Do a 10 to the minus 4th. Okay, and then also that will go. I'll continue that through 10 to the minus 7th. I won't make you suffer through that. But I'll show you. I can also do the other storm types that use that same time interval and time duration combination. So their next one would be the 6-hour MECs, and so we'll start that with a 10 to the minus 1, and same thing, I'll do that for all the 6-hour MEC storms. I'll also do it for the PMP storms. So I'm going to do a 2-hour local storm, 2-hour local storm PMP. Okay, and actually I'm going to rename that PMP so that I'm going to put PMP up front there, so it keeps all the PMP storms together. 2-hour local storm. Okay, and then I can do the same thing, copy for that, and do 6-hour local storm PMP and 24-hour local storm PMP. All right. Then similarly, I can I'll create a. Let's go ahead and do that. So now I'll create a new precip gauge, and let's use a different one that uses a different storm type that uses a different time interval and time duration. So up to components, time series data manager. This is where we're creating a new precip gauge instead of just copying them over. So I'm going to do a new precip gauge, and let's say that this one is for a 48-hour MLC storm type, and again we'll start at 10 to the minus 1 AEP. Okay, so we create that. Let's collapse these so we can see a little bit better, and then put that down at the bottom here in numerical order. Okay, so this new 48-hour MLC 10 to the minus 1 AP storm precip gauge comes in default here with cumulative inches, 15-minute interval, and this 1-day duration. So we're just going to edit that. We want to stick with cumulative inches, or actually it came in with cumulative millimeters. I changed that, I believe. Now, the 48-hour MLCs, if you remember from the guidelines table 8, I believe the time interval is 1 hour from reps. We just stick with that. And then the duration we want to be 10 days to allow 10-day simulation. And then we just are going to go to our spreadsheet, go over to our 48-hour MLCs 10 to the minus 1, and we're going to go down to a 10-day. We've extended the data out of reps Met Portal to 10-day duration, and then we're simply going to cut and paste that into HEC HMS. Okay, so that should line up, and again, just check that, and we have a, there we go, sorry about that, we have a key duration 48 hours and rainfall of 2.02. You can cross-check that against the Met Portal precip frequency table and curve, and then it's 72 hours. Met Portal extends the amount to 2.125. So just check that here. Yeah, at 2 hours or about 2 inches, and then extends it up to 2.125. All right. So then, lastly, let's create one more. I'll copy those over just like I did for the. I'm going to do for the others. I'll copy those over for the other 40 AEPs for the 48-hour MLC storm type. Lastly, let's create a precip gauge template for or the precip gauge for the 72-hour general storm PMP. Okay, so let's. Again, we're just going to call that one PMP and use that same naming convention we did above for the PMP storm. So 72-hour, this one is general storm. Just going to create that there, and then we're going to go down. It's groups it up here with these. And you know what? This basin has a tropical storm, or it's partial. The amount is less than the total. The basin average rainfall for the 72-hour tropical storm from reps is less than the 72-hour general storm, and reps uses the same temporal pattern for general tropical storms. So it's clear just by inspection that the general storm would be larger than tropical storm for any kind of volume control or long duration storm. So I'm not even going to bother running the tropical storm. And if you write that in a report, that's easy to justify just by showing the tropical storm and general storm amounts from reps. Okay, basin average rainfall from reps. Okay, so that's this one, PMP 72-hour general storm, and that again, it comes in incremental millimeters here. How I have HEC HMS set up. I'm going to switch to cumulative inches. That does stay at a 15-minute time interval. If you recall from table 8 in the guidelines that reps general storm PMP was developed with a 15-minute time interval, and again we want a 10-day duration for that long general storm simulation. And so that's it, and we'll grab that rainfall out of our time extension spreadsheet, 72-hour general storm, and that is in minutes, so it goes have to grab that from 0. I do believe, yep, it starts at 0. So we're going to grab that from 0 the whole way down to 14,400 minutes in 10 days. So we'll do that. And just paste those into HMS for the precipitation gauge. There, 1397. Goes up to about 14 inches in 72 hours. Couple notes here. We always have noted before that reps PMP tool labels this as 24-hour synthetic distribution. It's actually it is truly a 72-hour duration, 3 days, 14,400 minutes. Or I'm sorry, that was for the 10-day, extending to the 10-day duration, but it's a 72-hour, 43.2-minute distribution. It's just labeled 24-hour in reps because it was originally developed off of the core 24 hours of those general storms, using historical storm patterns. Okay, I want to show you just a couple other things really quick with reps storm output, just going back to that time extension spreadsheet and kind of looping back a little bit into reps. When we open the 6-hour local storm temporal distribution, and we would open this in Excel, but I'm just popping it open as a text file, and we have these 3 different temporal patterns, temporal distributions, this 10th percentile Huff curve, 90th percentile Huff curve, and then the 6-hour synthetic east. The reps guidelines tell you which distribution to use. We want to use this last one. So moving forward, in the model and in the reporting stuff, we only want to see that 6-hour synthetic east. These other distributions were just prepared as part of the rep study. They're not wrong. We just don't recommend using them in the guidelines based on what we've seen. And then the same is true for the general storm and tropical storm distribution. When you pop that open, you'll see the 10th percentile Huff curve, 90th percentile Huff curve, and then the last one will be that general storm synthetic distribution. Here it's east because we're in the east region, but there's also west of the continental divide. You'll see a west curve. All right, that's that. Now I'm gonna go offline and copy the rest of these to build out all our AEP storms for each storm type. And the one thing I was thinking, I said that there were up to 26 storm types. That's actually a minimum for where all storm types are applicable for if you're doing an IDF study or and hydrologic risk analysis, where you have probabilistic storms and PMP storms. Okay, I was thinking it may be a lot more than that if you have subbasins, if you've divided along a reps climate region and want to show, we talked about all that in section 4, the reasons you might want to divide, do semi-distributed rainfall and get different subbasin estimates for reps PMP. If you're doing any kind of more semi-distributed rainfall. It gets to be a little tedious. Our general recommendation is to do fewer subbasins, use basin average rainfall, and then to calibrate the results. We can adjust things later on in the calibration. But we talked in section 4, there are definitely times when you need to do subbasins and semi-distributed rainfall. And then you may also have historic rainfall events that you're going to use for calibration if you're lucky enough to have that historic rain data. We talk about that in the guidelines, that sometimes those historic storms that were used in reps, if they fell in your basin, we can get those from the meteorological consultant, or we have some of those, or your client may pay to have historic rainfall reconstructions for event calibration. So that would be another precip gauge you would be creating, is historical rainfall. All right, I'll check out and go offline and create the rest of these storms, and then I'll show you what this looks like when all the precip gauges are built out for all the reps design storms. Okay, we're back here, and I just copied and built out all of the precipitation gauges for all of the reps design storms, and that was just by copying and then copying over the precip gauges that we had with specific duration and time interval combinations, and then cutting and pasting the extended reps time series from our spreadsheet. Okay, so here you can see there are have the 26 storms of the probabilistic storm types 10 to the minus first through 7 for local storms, MEC storms, MLC storms, and then I have 4. I guess I probably have 25 storms here total. As I explained before, I did not include the tropical storm, but I have 2, 6, and 24-hour local storm PMP and 72-hour general storm PMP. Now, I added one other one that's going to be useful and that the guidelines talk about. Because we're doing partial area analysis, this basin exceeds some of the reps storm area size limits. So it's going to be useful to put a 0 gauge in some of the sub basins for the storm types that require partial area analysis. All right, so I went ahead and created I just called it a dummy 0 rain gauge, and that has the same duration as the local storms, the 2-day duration, because the local storms are the ones with the storm area size limits and reps, and then that is simply zeros. And I went ahead and did one other thing. Just I replaced the time series extension spreadsheet on the Google Drive that you can link to from the guidelines hyperlink, and I went ahead and put a tab in there for a dummy 0 gauge. Again, nothing fancy. It just makes it easy just to grab those zeros for 2880 or 2-day duration and cut and paste them into HEC HMS for a dummy 0 precip gauge. So just trying to make life easier and make this process as efficient as possible. Okay, so next, what we're going to do is create those are the precip gauges in HMS time series. Next, we're going to create the meteorological models that associate the rainfall with subbasins and also handle annual evaporation at the same time. So let's flip back to the guidelines real quick and just check back in where we're at. So we did section 7.3 and the precip gauges. Now we're in section 4 with the meteorological model set up. Again, just for another pro tip, just for efficiency, create one gauge, create one MET model, do the annual evaporation, and then copy that over. And then where we have partial area analysis, set that up and then copy that to any other storm types that use the same partial areas. Okay, let me blow by these figures 9, 10, and 9 and 10 anyway, and I want to show you what that looks like on a figure here. So where we would set up the partial area, we'd have the dummy zero rain assigned to subbasins that don't have rain, and then the partial areas would get their storm precip gauges, so as specified hydrographs. Okay, so we'll go through that. I just wanted to, there's a figure of it in the guidelines. The other thing I wanted to touch on that's in section 7.4 is we do mention that here what we described is you could alternative to building out all these reps precip gauges and a different MET model for each reps design storm. You could simplify that by just using the unscaled temporal pattern from reps MET portal for each storm type. And then all that happens is those unscaled patterns get scaled by the AEP precip frequency estimate. So you could handle that, just have 3 precip gauges, 1 for each storm type, 3 MET models, and then handle it in HEC HMS under the compute tab, and there's a precip ratio that could be specified. So you could just put the precip frequency estimate for each precip ratio. What we explain in the guidelines, I mean, it's just user preference, and we're not saying one's wrong or right, but but what he said is that this simulation scaling, handling the specific AEP amounts in the simulation end, it saves a lot of time in model setup, but in my opinion, it tends to be more difficult in terms of the analysis and documentation, because then every time you want to look back at specific results or document something, you have to rerun that storm for the appropriate scaling. And I think it's probably too more prone to errors. So this way, everything is set up and locked in, where it can be checked and QC checked and documented and stuff. So anyway, just that's there. If you want to use it. Okay, and then I guess lastly what we say here is if you do set up all the individual storms like we're recommending here, then the precip scaling can be reserved for our dam safety rule 7.2 atmospheric moisture factor, which is required to be applied to all inflow design floods. This 1.07 factor to account for expected future increases in atmospheric moisture over the assumed 50-year design life. So that's for design floods, for doing IDF studies. Okay. All right. So let's get out of the guidelines then, go back to HMS, and we're gonna create MET models. I've already started one here I just started for the PMP 2-hour local storm. We have specified down here in the options, then I've precip by specified hydrograph, and that's going to allow us to link to those precip gauges that we created, and then evapotranspiration, it's annual evapotranspiration. Let me flip back to the guidelines too, and let's go back to section 6, that's master summary table. And this is where this is really handy. It just, hopefully, it gives a summary of all methods and then parameters to use. So here under meteorological models, we're using precip specified hydrographs and annual evap as the methods, and then the precip hydrographs get linked to specific design storm precip gauges, the annual evapotranspiration. We're recommending the parameter value of 0.098 inches per day, and that was from the CSU research study, just from a experimental area that they have in the Prudhoe Valley, so Prudhoe River Valley. So we have here annual evaporation, just for each subbasin, 0.098%, pattern none, and then for specified hydrographs, then we're going to go in and do this, link each subbasin to its precip gauge for this 2-hour local storm. But here, this is going to be a partial area analysis as a PMP local storm that has a recommended size limit of 100 square miles. So next we'll do that, and I'll show you where we'll use that dummy zero rain gauge for the partial areas that don't include rain, and then the appropriate 2-hour PMP local storm precip gauge for the partial area where it does rain. All right, so yeah, let's set up this specified hydrograph for the 2-hour local storm PMP. As I said, it's a partial area because the REPS has a recommended storm area size limit of 100 square miles in the east, at least in the east, for PMP local storms. So what I'm doing is doing a partial area analysis for our Lake Meredith example basin here. And it's handy here, I just split the screen and I pulled up, I mentioned at the beginning of this that one of the inputs that'll help set up the model is this partial area table if you're doing a partial area analysis. May not be necessary for a lot of smaller basins, but if your basin does exceed the REPS storm area size limits, then it's going to be necessary. So here, if I pull up this table in a split screen, easily just shows which basins I'm assigning rainfall to by REPS storm type. So here we have PMP 2 and 6 hour, 24 hour. So it's all my local storms, and then no limits on the general sizes storms, and then precip frequency local storm has a different size limit. We'll get to that in a minute. Right now, let's just focus on this 2 and 6 hour PMP. So subarea 1 is getting the dummy 0 gauge. Subarea 2 gets the dummy 0 rain gauge, and subarea 3, and then subarea 14. Okay, so those are the areas excluded from this 2-hour from the PMP local storm. Then I can just go in and assign the precip gauge for the rest of the non-zero subbasins as that 2-hour PMP local storm precip gauge, where we entered the REPS rainfall time series. Okay, so it's super easy. We're doing, other than the partial area, we're doing uniform basin average rainfall, not doing semi-distributed sub-basin rainfall in this case or anything like that, just uniform basin average rainfall from the REPS PMP tool, 2-hour local storm. Okay, and just check that subbasins 1, 2, and 3 and 14 get 0, and then the partial area is the remainder of them for a 2-hour local storm. Okay, now with that saved, now with this partial area template set up, I can copy this over for the 6-hour PMP and 24-hour PMP, and then just easily change those the specified hydrographs for the subbasins that get rainfall. Okay, yeah, so now that this 2-hour local storm PMP meteorological model is set up with this partial area, and I can easily just copy that over to a 6-hour PMP local storm meteorological model, because the PMP local storms all use the same partial area. They all have the same, the local storm has the same REPS storm area size limit, so it's all the same partial area. Let me just flip to that really quick just to remind, because that was back in section 4. We talked a lot about that. But if I flip back to my reporting from my subbasin properties reporting that we went over in guidelines section 4, I have a map here that shows so this is, above it is our entire basin, 200 some odd square miles. And the REPS recommended storm area size for partial for local storms in the east is 100 square miles. So we selected the subbasins that totaled about 100 square miles, 106 square miles here, and it's this partial area. So in the rainfall meteorological model in REPS, when I ran the REPS PMP tool, I only ran it for this partial area, and so it only returned, you know, the aerial reduction is done by depth, area, duration tables, and it used this partial area to get PMP. So the REPS local storm PMP only applies to this partial area here. And so when we're loading that, when we load that as a precip gauge into HMS, it's only applicable to these subbasins. We tell HMS, HEC HMS, that in the meteorological model. So we're telling it there's dummy zero gauges, zero rain in the subbasins 1, 2, 3, and 14, and then the REPS 2-hour local storm PMP precip gauge is only applicable to these subbasins in the partial area. Okay. All right, so let's just give you a visual on that, just to remind you why we're doing this. Okay, so then we set up this this partial area for the 2-hour. It's exactly the same for the 6-hour and local storm PMP, and actually the same for the 24-hour also. So all we got to do is the partial area, that is. The precip gauge is different, obviously. Okay, so we're now going to change that to PMP 6-hour local storm, and this is, again, the meteorological model. So we have a copy of that. The annual evaporation is always the same. That's uniform for everywhere from our hydrology guidelines from the CSU Mountain Hydrology Study. And then we go to the specified hydrographs for the 6-hour local storm PMP, and all the partial areas are already set up. All we have to do is change the rain gauge to 6-hour local storm PMP, the rain gauge, the reps time series. Okay, so that's easy enough that I can just do it on the fly here, and then we'll 6-hour on all those. Okay, we'll save our model and copy that over and make it into a 24-hour local storm PMP meteorological model. Same thing. Annual evap 0.098 inches per day stays the same, and specified hydrograph, the partial area stays the same, and all we do is change the REPS time series precipitation gauge in HMS. PMP 24-hour local storm PMP, way down for all the applicable subbasins within our partial area for local storm PMP. Okay, 24-hour. Okay, so those are good. All right, so now we can do the general storm. Or no, sorry, there's one more. There's a different partial area for the REPS 6-hour MEC, or for the, I believe it's for the 2-hour local storm precip frequency storm. Let's go back to our reporting and look at the maps. Okay, so here we have the partial area for REPS Met Portal 2-hour local storm precip frequency, and that, I think for the precip frequency in REPS, the storm area size limit's 200 square miles. So I added more subbasins to get something around that 200 square miles. But below in the Met Portal tool, it absolutely has. It's a hard limit. It has to be below 200 square miles, or else the tool, the REPS Met Portal tool for precip frequency uses stochastically generated areal reduction factors, and they stop, in this case, for the eastern macro region 2-hour local storm, they stop at 200 square miles. So if you try to run Met Portal for, in this case, for a bigger area than 200 square miles, it will not return the 2-hour watershed average 2-hour local storm precip frequency. Okay, so that's what's up with that storm area size limit of around 200 square miles. And then the other ones don't have storm area size limits applicable to this basin. Okay, so it's just this. Let's do the 2-hour local storm precip frequency from Met Portal next, and it's let's just go ahead. We could copy it over, but let's just, to make the point that this is a different partial area, let's just go ahead and create another meteorological model for this. Okay, so this one is going to be the 2-hour local storm, and now we're talking about AEP storms. So we're going to go ahead and do a meteorological model for each AEP, probabilistic storms for each AEP for each storm type. So we'll start with the 10 to the minus first 2-hour local storm for Met Portal. Okay, and we'll set that one up, and then we'll just copy it over and change the precip gauges. Okay, so this one has different partial area. Let's go ahead and let's reopen our partial area table. If we go back to our reporting here, just do a split screen. Okay. All right, so hopefully you can see that. There, let's do it that way. Okay, so now we're next we're moving over to the Met Portal precip frequency storms, since that's also a partial area analysis. We'll just knock those out first. So this local storm, you can see here, the only subbasin we don't include in that case, in that roughly 200 square mile storm area size limit, is subbasin 2. Okay, so let's get rid of, just collapse these PMP local storms and move on to the AEP Met Portal precip frequency. Again, we're going to have to add annual evapotranspiration. Okay, and we have precip by specified HEC graph. That's right. And units are customary U.S. customer units. That's right. And let's do subbasins. Include subbasins. Annual evap is 0.098 there. Let's just do a bunch of 0.098s and copy those in. Okay, so 0.098 for annual evap, no inch per day, no percent pattern, spatial pattern. Okay, then on to the specified HEC graph. Again, back to our partial area table for Met Portal precip frequency 2-hour local storm. We want 0 rain in subbasin 2, where the black box is here that blacked out. Okay, so that's dummy rain. All the rest of them, we're going to go with the precip gauge for the applicable storm type and AEP 2-hour local storm 10 to the minus 1. Okay. Okay, so do that, and partial area for the 2-hour local storm, precip frequency, probabilistic storm, 10 to the minus 1 in this case, and we again have to we're going to create 25 storms here, 21 probabilistic storms, and then our 25. We're going to do 21 probabilistic storms, and then our 3 reps local storm PMP storms and 1 general storm. We're not doing the reps PMP tropical storm, as I discussed earlier. Okay, so this is going to be super easy to copy over, and just to do 10 to the minus second and through 10 to the minus 7th, and then obviously a partial area stays the same for all these 2-hour local storm precip frequency storms. The only thing we have to do here is change the AEP for the precipitation gauge, the reps time series, temporal rainfall temporal distribution that we created. Okay, make sure we hit all those. And this is where this gets probably to the point where you just need to put on some good music, and this just takes some time to do. So we're going to create. Definitely won't make you suffer through this in the video, but I'll check out here again and just create, build out these 1 through 10 to the minus 7 local storms, and then the meteorological models for the other storm types, the 72-hour general storm PMP, and then for the 6-hour MEC precip frequency storm 10 to the minus 1 through 10 to the minus 7, and 48-hour MLC 10 to the minus 1 through 10 to the minus 7. Those are all full areas, and so those are not going to require partial area. And I'll come back and I'll show you what I did for those. But let me check out now and just build these meteorological models out, and then we'll be ready to move on to the setting up the actual basin model. Okay. Okay, I'm back, and I've offline. I built out all these meteorological models for all of our, in this case, for this example basin, 25 different reps design storms. So I had the local PMP storms built. Now I have a MET model, meteorological model for the 72-hour general storm PMP, and the difference here is that there is no partial area. There's no rep storm area size limit for general storms. These are giant synoptic scale storms. So it applies to all subbasins, and then we simply go down through, after selecting subbasins, we simply go down through and pick the PMP 72-hour general storm precipitation gauge reps time series that we created for the 72-hour general storm. Okay, and remember this, in this case we're using spatially uniform rainfall for the entire basin here, not semi-distributed sub-basin rainfall. We're using basin average rainfall from reps PMP tool. Okay. Then we get into the, I had already created the 2-hour local storm 10 to the minus 1 and copied it over 10 to the minus 2. So I just continued that through 10 to the minus 7. In each case, all I had to do, the partial area was already set up. All I had to do is just go in and select the correct precipitation gauge for the correct storm type and AEP. Okay. And then just finished off with doing the same thing, creating a meteorological model for the 6-hour MEC storms, 10 to the minus 1 through 10 to the minus 7, and 48-hour MLC, 10 to the minus 1 through 10 to the minus 7. Those did not do not have storm area size limits that were applicable to, that limited this basin that we were looking at. So those are applied to the entire basin. So 48-hour MLC 10 to the minus 1 specified height graphs are just for the entire basin, just the precip gauges that we created for the correct storm type and AEP. That's 10 to the minus 1. The next one's 10 to the minus 2. So there's, like I said, we have 25 total storms here, 25 design storms, 25 different meteorological models that use 25 different precipitation gauges. I indicated earlier, there are some other ways to do this, or at least one other way that I know of, that by scaling these AEP storms in the compute tab in the simulations. I prefer to do it this way, where actually lock it in with each storm having its own meteorological model and precip gauge. But I already talked about that. And then the only other thing I'll mention here is just a nod to QC checking. I'm going to talk about that at the end, but there's obviously a lot of data here and a lot of manual entry and copying over. So it's pretty imperative that you go through and QC check your model. And here, I mean, we'd be looking that we have the correct partial area for each storm type, and then let's say looking at an AEP storm, that we have the correct partial area, and then that we have the correct storm type for the gauges where there is rain, the correct storm type and the correct AEP for each one. Easy to make a mistake there. And there's lots of other opportunities to QC check too. When we get the results, you should be checking the model computed rainfall for each simulation against the reps rainfall totals to make sure that you have the correct storm in for each simulation. And that's it. So hopefully, we're done with, it's been a lot of work, but we're done with getting the design storms into the model, setting them up as precip gauges and meteorological models. It's a lot of work, but that's it. That's the driving, that's the forcing function in all of this hydrologic rainfall runoff modeling. So the only other time we're going to see all these storms is when we go to the compute tab. I'll do this later on, but go to the compute, create the simulations. Then the way I do it, as I said, I'm going to build out separate simulations for each storm. So then we're gonna see these 25 again as I build out this 25 different simulations. Okay, but for now we're gonna go to the actual basin model and enter in all our parameters that we have from our effort so far for the soil moisture accounting loss method, Clark unit hydrograph, route transformation method, and then for reach routing. So what I said there, the last piece of input we need from our sections 4, 5, and 6 efforts so far is this table 6 from the guidelines that we filled in for our basin that lists all this kind of this master summary table that gives all of our parameters for the model. So this is going to be our friend. As we go down through here, we did meteorological model, precip gauges, and annual evap. Now we're going to move to basin model, and this is going to be our friend as we just go down through each sub-basin and set the methods, and then fill in the parameters here by sub-basin. So I'm going to just have this on one screen, and then we'll go down through and fill in the sub-basins. I'll just show you a few examples of those, and again, then I'll check out and finish the model. All right, let's check back in on the guidelines. So we're in the Hydrology Guidelines. We're in section 7.5, basin model setup. The sub-basin elements, the text tells which methods to use in HEC HMS: canopy method, simple canopy, loss, soil moisture accounting, transform, Clark unit hydrograph, and base flow, linear reservoir. And then there are figures. Figure 4 shows those methods to use under each sub-basin. And then the text again repeats this using table 6 to facilitate easy parameter input and going through each of the methods and setting the parameters. Okay, so let's go back to our model and our table 6. I'm going to split screen these. Usually I'd have them on 2 screens, but I just split screen this so you can see them in the video. But first, let me make table 6 bigger to remind you of that. I did. We have our different methods, and then under basin, simple canopy, SMA loss, Clark unit hydrograph, and then for base flow, linear reservoir base flow. And I also put at the bottom, created an area just to do your reaches. Those are separate, not by sub-basin, but by reach instead. I'm just gonna split screen that so that we can page over while I have it here on the screen. And we're going to start with sub-basin 1, go back to our HMS model. And if you recall, I did not hear what I was saying earlier is we could have set the proper methods by our guidelines under tools and then program settings and defaults. We could set all these methods: simple canopy, SMA loss, Clark unit hydrograph, and linear reservoir base flow. I did not do that because I have a new version of HEC HMS and I hadn't gone in and set those yet when I initially created this model. So that's fine. It just gives us a chance to go through and see actually setting those methods. So let's pick sub-basin 1, and then we would have to go down here in this case and manually set the correct methods that we're using. So canopy method, discretization method, non-canopy method, we have simple canopy here, okay? And then each time, it's just going to ask it, it's going to change the method and overwrite the data. That's fine, of course. Snow method, nothing. Surface method, nothing. Loss method, we're doing soil moisture accounting. It's already on Clark unit hydrograph method, so that's good. And the base flow method, we're doing linear reservoir. Okay, so that's that. The correct methods are set. Now we can just tab across and put those parameters in. So here in our table 6 Excel spreadsheet, looking at subbasin 1 here, and so the initial for canopy method, simple canopy initial storage is 0, max storage is 0.169. I'm not going to talk, we've already beat this up as far as what these parameters mean, where they came from in the previous sections 4, 5, and 6 videos and the guidelines. So I'm not, at this point, all we're doing now is filling in the model. I'm not going to talk more about what they mean or where they came from. Uptake method does have to be set to simple, and that's not actually in the table, but it's in the figures, screenshot figures in the guidelines. So uptake method simple. Loss method. So now we move down to the SMA loss part of table 6. So soil percent is the initial soil moisture, 23.763 here. Groundwater 1% 0, groundwater 2% 0, max infiltration we have 0.804, impervious we have 5%, soil storage we have 21.841, tension storage we have 4.512, soil percolation we have 5.60, groundwater 1 storage 2.427, groundwater 1 percolation 0.1 inch per hour, groundwater 1 coefficient. Scrolling down here, our table 6, groundwater 1 coefficient is 10.41. And then the rest are zeros. Everything from groundwater 2 is 0, 0, 0. Okay. And of course we can check all this, but it's all going to need to be checked anyway in terms of QC checking. All right, so now we're on to unit hydrograph response for subbasin 1. That's Clark unit hydrograph. Standard method, so meaning it's just a constant parameters instead of variable parameters that we'll talk about later. But for now, we're using the standard method. Time concentration for subbasin 1 is 8.10. Storage coefficient 3.47 and default time area method. Then base flow linear reservoir. We're down here in table 6 for subbasin 1, reservoir 1 discharge, initial type, initial groundwater 1 flow is 0, fraction we leave blank. Groundwater coefficient is 10.41 hours again, and that's it. So your subbasin 1 is set up. Okay, and then all we're going to do is fill out the rest of those basins, just panning over in our spreadsheet, subbasin 2, 3, 4, filling in all those parameters. Okay, let's do a reach just to finish this out. And so in this case, the first reach I come to is reach 4, going downstream, or starting at the upstream end. So reach 4 parameters I have in my spreadsheet here. That has to be set to Muskingum-Kunge method. Okay, and gain loss method is none. The routing parameters we have here that we just came directly from HEC HMS when we did the we went up here and did the parameters, characteristics, and reach. So this was pretty easy. We put it into a table and then copied that table into our table 6 summary. Okay, so reach 4, we're at here, length is 1.44630. The slope is 0.00520 feet per feet. To Manning's M, I'm just going to assign right now is 0.035. And the initial flow, we're going to get that. The guidelines talk about using that as a bank for using a 2-year frequency flow. I have that from Stream Stats. I did not fill that in the table here. I guess you could for completeness if you wanted to. And then the channel cross section I'll just get from LiDAR data and cutting a cross section in ArcMap. So I'm going to leave this blank from now. But that's all the parameters that we generated for soil loss method. Well, simple canopy method, soil moisture accounting method, Clark-Union hydrograph transform method, and then reach routing. That's all the parameters we generated from using HEC HMS to set up, to process the terrain and create the sub-basin and stream network. Then the CSU SMA method to get loss parameters, and our Clark-Union hydrograph spreadsheet to calculate Clark-Union hydrograph parameters. Okay, so that's that. I'm not gonna do this, fill all this stuff in the video. I think you get the idea, and then I'll go down through here using table 6, fill in the rest of this, and then check out here, and then I'll come back with this model filled in. And the last step we'll have to do is create control specs in the components here, and then we're going to go to compute, create the simulations, and we'll be ready to run. So it's pretty, at this point, after everything we've done, hopefully it should be pretty easy to create the model and get it up and running. Okay, so I checked out and just filled in pretty much all the rest of my basin model here from our table 6. Again, a couple things I realized I'm going to try to go back and hit. But first I want to I'm going to go through one more sub-basin with you, just to make sure that's totally clear. It's pretty easy, but just go through it again. So the last one here, I'll fill into sub-basin 16. I go to my table 6 that I filled in from all the parameters we estimated along the way here for my sub-basins. And just a reminder that sub-basin, table 6 is the descriptions are all in the guidelines as the table 6. That's why we refer to it as table 6. But then there is a template. There's a template in the guidelines. So this is that summary table in section 6.7. This was in the section 6 tutorial video, but just reiterating it here since we're using table 6 heavily here in this video, section 7 video. Summary table, parameter estimates, table 6, link to the sample spreadsheet. So we're not asking you to recreate that. You're welcome to use the one we already created. Okay. Then I'm going to come back to this in a minute. But for right now, let's go to my table 6 that I've created for my basin. And sub-basin 16. So I split the screen in Excel. I'm going to scroll over to sub-basin 16. Now, if you remember, I didn't set the methods under my program defaults, so I get to go down through and manually set these. Canopy method is simple. No surface method, loss method, soil moisture accounting, Clark-Union hydrograph and recession. Baseflow method is linear reservoir. So then we come up to the sub-basin element, and we're going to fill that in, scroll across from our table 6 that we filled in. Initial storage under canopy is 0, the maximum is 1.169, and we have to remember to do a simple uptake method, only in dry periods. Loss, then going down in our spreadsheet here on the right, initial soil moisture is 56.083, groundwater 1020, max infiltration is 0.339, impervious is 5%, soil storage is 15.190, tension storage 9.136 inches, soil percolation is 0.043 inches, groundwater 1 storage 1.688 inches, groundwater 1 percolation is always 0.1 inch. Scroll down in our spreadsheet here to keep going down through the parameters. Groundwater wind coefficient 3.75. hours. The rest of these are zeros. Then we go to the next method is the runoff transformation, Clark-Unit hydrograph standard method. From table 6 here, the time concentration is 2.91 hours. Storage coefficient is, the R is 1.25 hours. And then linear reservoir base flow method, we have discharge type, initial groundwater when discharge is 0, fraction we leave blank, and the groundwater coefficient is 3.75 from right here in the spreadsheet. Okay, and that's it for the subbasin parameters. Okay, so that subbasin's done, and I usually blow through those pretty quick because, save that in HEC HMS, because we're going to go back through and QC check this all later, and I'll show you what I think is a kind of an easier way to QC check it rather than just going through tabbing through every element in the Watershed Explorer. Okay, so now I want to go back and talk about reaches. I'm going to get rid of this or minimize this spreadsheet for right now. I realize reading through the guidelines, we give a little bit of short shrift to reach routing, and I tend to not think that model results are overly sensitive or very sensitive to reach routing, but I just had a model that we did where the results were, peak flows were very sensitive to reach routing, and so at least in the video here, maybe in future versions of the written guidelines, we'll beef that up. But at least here in this video, I want to give a little bit more of time to the reach set parameterization and setup here. Okay, so I'm going to go back to reach 3 in my model here. This fairly long reach through here, and I'm actually I have reach 2, 3, and 4 that I'm going to treat the same. They're all part of the same creek here, which is the main tributary creek to Lake Meredith. It's called Bob Creek. And if you go back to my section 5 reporting on subbasin properties, I printed a map for reaching. If you look at the reporting requirements, it asks for a map of the subbasin reach structure in HMS. And so we can see here, reach 2, 3 is here, reach 4 is here. I'm going to show you how we set these up as actual reaches with Muskingum-Kunj method. And I'm also going to talk about this side, reaches 5. Reach 6 is a little one up here, and then reach 5, 7, and 8, which you can see here go through the reservoir. And that's a little bit of a different case here. Actually, in this came up in the reach setup when I started looking at that in detail. And I think that could also come up in your your QC checking for your subbasin properties and model, just to make sure that what HEC HMS has created here is from the terrain when it comes up with this stream network and subbasins, make sure the QC check that what it's created is reasonable and accurate. Okay, but let's first talk about this, setting up this reach 3. Parameterizing it. Okay, so what the guidelines say, if you go where it pretty much the only place it shows up, it is in text, but it gives, like I said, maybe short shrift to reach routing. But in the table 6 in section 6 of the guidelines, the last method it has is the Muskingum-Kunj reach routing, and then it talks about the parameters and the recommended values. So we have length and being in feet, initial type discharge, Manning's N, using literature values. There's some textbook values from Chow or from from HEC-RAS, wherever you want to pull those out. Index method, and then the index flow. We say here to use the 2-year 50% AEP estimate. So what we typically do is just grab that from Stream Stats. Now the reason we say that is because that's what CSU, Colorado State, did in their mountain hydrology research study. If you read through the HMS guidelines, you might get different ideas, but for right now, at least initially, we're using that value, and then that could possibly be calibrated if you wanted to. But that's an easy way to do this. That's what CSU did for their development of this modeling method. All right, so then shape, trapezoid or 8-point. Well, typically, I'll show you a method for 8-point. We just say that you can cut transects from the DEM. Okay, so I wasn't planning on doing this originally, but I think it's probably worth going through. Again, this is not, as I've said many times through our sections 4 and 5 tutorial videos, this is not intended to be an ArcMap tutorial, but I want to show you enough that ArcMap is not a limiting factor. We don't want people to be this method does rely on ArcMap, and we don't want people to be derailed by that. All right, so if we're going to cut cross sections for reach routing from the DEM, one thing we can do is get LIDAR, look for LIDAR data. So we typically go to our sister agency, Colorado Water Conservation Board, hosts this Colorado Hazard Mapping and Risk Map portal. Here is the website, or you can just Google that. Then I've selected a map set that's for my region, and then I told it to show the tiles. So I selected, these are different regions that have been mapped. I selected this one that's applicable for Lake Meredith is right here. I told it to show the individual tiles, and then I went in to where my reach 3 is. Again, in my model here, reach 3, I wanted to grab a typical cross section somewhere upstream here of the Highway 96. I felt like was a typical reach. Keep in mind, remember, this is not HEC-RAS hydraulic modeling. We're choosing one section that represents a long, several mile reach here for routing purposes, and we could do more. But that's this is very, in my estimation, this is a very approximate thing. So I picked LIDAR tile here that I thought would give me a representative cross section. I can zoom in there, and there you can see is Bob Creek, and I'm going to take my cross section through here. So I selected that. This menu on the left, or window on the left, comes up. I select DEM. You can download the metadata too, or a point cloud. Hit download. I went to download my downloads, opened that up in ArcMap, and imported that. So I created a folder for Reach LiDAR, and then that just came in as a TIFF file. Now, it does not have, what I've found is these LiDAR DEMs from the CWCB website do not have a projection assigned to them. You can look in the metadata. My experience is that they've generally been UTM NAD 83, zone 13. So what I do is go into the ARC toolbox under Data Management Tools, Projections and Transformations, Raster, Define Projection, and you just double click on that ARC tool, pick the LiDAR DEM that you downloaded, and for us it's this USGS OPR Colorado Central Eastern Plains. So I picked that. I've already done it, but before this came up as no spatial reference. So I just go in here, select a projection, projected coordinates, UTM, that's NAD 83 is what I wanted, and then 13, zone 13. Okay, hit OK, and that assigns that. So now it comes in the DEM, this DEM tile that I downloaded comes in the right place. Okay, so next, in order to cut a cross section, what we're going to do is use the 3D Analyst tool, and hopefully you have that. If you do, so make sure it's turned on under Customized Toolbars and then Extensions. That 3D Analyst needs to be turned on, and then you can display the toolbar on your 3D Analyst on your the top. And what we're going to do then, make sure that we have that DEM selected as the applicable layer for the 3D Analyst tools. Use this interpolate line, and I drew a cross section. It's really simple. Just click, 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 and I wrapped it around perpendicular to the terrain, cross a perpendicular crossing the stream where I want this representative reach. So I drew the line with interpolate line. Next, I went to 3D Analyst and did options. I gave it a folder where it's going to save the cross-section data, and again, I just used the same folder where I downloaded the DEM to. And again, as we've always said before, things just work much better if you work off a local hard drive, so a C drive in this case, instead of working off a server or the cloud or what have you. So ArcMap just seems to work a lot better. So I'm saving this to a local hard drive. I tell it where to save the profile graph data, and then lastly, I go into this button here, point profile, select, pick the down arrow, and sorry, I have to select with the select arrow. I have to select that section, and then it's going to allow me to do the profile graph. Okay, so there is the cross section that is in the cut through this LiDAR terrain. At my stream cross section. Next, what I did was open that point file, the section profile point file that it created, and that's what these little dots are along. So see if I turn this off, you're seeing the actual section I drew. So these dots are the points that it cut along the LiDAR terrain. If I open that attribute table, I get the M and Z points, which are station, horizontal, and then in feet, and Z is in meters. So I download those, or I download those by, export those. I go with, once I've opened the attribute table or the data, I just export those, and we've done this before when we were doing our subbasin properties, but just create a text file here, and I did that and saved this as reach 2 cross section. It's actually reach 3, but I'm going to use it for reach 2, 3, and 4. Reach 2 cross section data. Okay, and then once I have that as a text file, then I went into open that in Excel. Okay, I opened the reach text file in Excel, or that cross-section text file in Excel, and I just created a column and converted my meters to feet. I graphed those, and that's the blue line, so that's easy to compare just as a quick QC check. That compared well to what came out of 3D Analyst and ArcMap. And then I just went down and picked breakpoints to define an 8-point cross section for Buckingham Conch. So you can see here I just created a column, and then I labeled those as points 1 through 8. Grabbed those 8 points and made myself just an abstracted 8-point section, and that's the orange line, and you can see overlaid here. I think that's a pretty representative cross section for that read. With that, we can go back to HEC HMS, and let's split the window again with our table 6 actually. And I'm going to go down to the reaches in table 6 at the bottom. At the bottom there, I had those. Told you I had the separate rows that are not by subbasin but by reach. So here we're in reach. We're doing reach 3. You'll notice if you were paying attention before, I had actually written the mile lengths in here. This is supposed to be HEC. Once I started entering the data, I realized that HMS is asking for length in feet. And so I had to go back to our reach properties table that we created in section 5 of the guidelines. We got it from HEC HMS. But when you go in parameters, characteristics, and do a reach table, it gives you that length in miles. So in the spreadsheet that we created in section 5 of the guidelines, in section 5 tutorial video, we just simply converted that to feet. So I needed to, I'm going to close out of that. What I needed to do is then write those feet in my table 6 summary table, because that's what HMS is looking for. Again, I mean, it came up clearly in the model during this model creation step. If not, it would have come up with my QC checking. So reach 3, set the method, Musqueam Conge, then tab over. See, I had originally had it as miles. Now I'm going to change that to correct that to feet 57,457 feet. The slope is 0.00219, comes right from HMS from its terrain processing that we did. I'm going to use 0.03 for the channel, straight, relatively straight, open channel. Index methods flow. For the index flow, again, I'm going to go to stream stats, and we've generated stream stats for this basin, and I'm just going to use it for the entire basin. I mean, you could subdivide it up and do different reaches if you wanted to. Stream stats looks at different regions, and then it gives you the area averaged. Flood frequency estimates, we're looking for that 50% flow here to get the 2-year ARI flow, and so the value is 429 CFS. So by the method we have, by our guidelines, that 2-year flow is going to be our index flow, 429 CFS. I'm going to go do an 8-point cross section. It's going to ask for a left and right overbank Manning's End, and this is pasture grass, so I'm going to do 0.035 Manning's End, which I got from Chow. Cross section is, I've created one, it's 234. I'll show you that. This invert is optional, you don't need that, so I'm just going to leave that blank. Okay, so that's reach routing by Musqueam Conge, 8-point cross section. Let me show you how I did, just to wrap this up, how I got the cross section from ArcMap then in Excel into HMS. So it gets created under components, paired data, okay, and you scroll down and you have cross sections. I created a reach 234 cross section, okay. So let's go down to my paired data in my model in the Watershed Explorer, cross sections, reach 234. I described that manual entry, it's in feet. I took, again, let's do a split screen here, but now I'll go back to my LiDAR 3D Analyst cross section that I extracted from 3D Analyst. Okay, scroll over my abstracted 8-point cross section, which was the orange line, right, is over here. So all I did was cut and paste these 8 points, I graph those, and we can get again just a quick QC check that's looks like the same cross section as I developed here in Excel for reach. I'm using it to represent reaches 2, 3, and 4. Okay, so I think that gives process to attention to reach routing by our method. The only thing left is here in the components is to set up our control specs. So let's just go ahead and do that, and we'll be finished with the model setup. So we want generally two, what we say in the guidelines is 2 control specs. We'll be fine. We basically just have a local storm control spec, which is the 2-day simulation, and a general storm control spec, which is going to be the 10-day simulation. So then it creates those under control specs. We go to general storm, and then we're just going to start, since this goes back to the precinct gauges, it defaulted to January. So we're just going to start on January 2000, just as a default, since these are design storms. It's not event calibration. It's just a fictitious date. Start that at 00. And if you remember, we went through for general storms, we wanted a 10-day simulation duration because we usually have a significant amount of water going into the ground and returning as subsurface flow back to the stream hydrograph, and we want to give that a chance to return. Those are long lags that groundwater 1 coefficient, and then the linear reservoir coefficient on the order of several days, can be 3, 4, 5 days. So we want to run that out to let the hydrograph return to about, we said, within about 5% of the peak flow before we end the simulation. All right, so that's up to the 11th of January, and what we say in the guidelines is run the general storms at a 5-minute simulation time interval. So 5 minutes there, okay, and then just choose local storm. Start that on January 1, 2000, and that's just a 2-day. What we recommend is a 2-day simulation there. And that's how we set up all our precip gauges. Ending that at 00 hours on the 3rd, and that for local storms we say to do a 1-minute computation interval, time interval there. Okay, so that is it. The model is done, and next I'll come back and we'll set up the simulations. We'll set up the simulations under the compute tab. All right, so yeah, this is our finished model. Just if you're not super familiar with this, just to take a step back. We have the Basin model. It has all our elements. We put in all the methods and parameters from our CSU SMA method, Clark unit hydrograph, Muskingum-Kunj reach routing. It's all here with the watershed model shown in the map viewer to the right. Then we did our meteorological models, which we created one for each REPS design storm in this case, PMP, and then the probabilistic storms. Those assigned precip gauges to specific subbasins, and they also have evaporation in per our guidance in the CSU method. We have control specs, a 10-day simulation for long general storms, 2-day for local storms. We have the time series data, which is the precip time series for all the REP storms, PMP and probabilistic, and then this dummy zero gauge to facilitate partial area analysis where our REP storms are limited by the REPS storm area size limits in the guidelines in our REP study. And then the paired data we had that gave us a cross section to do Muskingum-Kunj reach routing, and then the terrain data, which we originally imported from a USGS DEM and did the GIS processing here to originally create the stream network and subbasins. Okay, so that's that. The Basin model is finished. Now we're going to go to the compute tab and create our simulations. Here under compute, create compute simulation run. Okay, we're going to start with, let's just start with a 2-hour PMP storm, or they call that PMP. Is there a 2-hour local storm? And this wizard takes you through this pretty easily. We only have one Basin model. 2-hour local storm is our first rainfall. We want to use a local storm control specs or 2-day simulation on that, and that's it. So that's the first simulation we created here. You have options for where you save the DSS, the data. And then we can just copy that over, or we can keep going through that compute, create simulations. But the main thing, I don't think there's really too much of a difference, really. It's just we can do it both ways. If we create a copy, 6-hour local storm there. That, and then we would select 6-hour and then just go down here, and you can drop those options down. Basin model is always going to stay the same. In this case, the control spec stays the same. The only thing that changes is the meteorological model. Okay, so that's our 6-hour. And then you would now go back to the create compute and do a probabilistic storm. So this one we could call our 2-hour local storm 10 to the -1 AEP, and same basin, pick our 2-hour local storm 10 to the -1 AEP meteorological model and a storm, the local storm control spec, and that, and those could just be copied easy enough with changing the AEP for each of those, and just remembering to come down here to the bottom and change, whoops, make sure you're selected the right storm. So that one's still, so I unselected that accidentally. So that's our 10 to the minus 1, then select the 10 to the minus 2 simulation we created, and select the correct MET model. Everything else is all right. Okay, so I'm gonna stop there, and I'll just go offline, build all this out. But that's I'll create a simulation for each rep storm. So again, in our case, there are going to, I think we said 25. We have 25 storms. The 21 probabilistic storms, and then we have 4 PMP storms, 2, 6, 24-hour local storms, and then 72-hour general storm. I will create a simulation run for each of those. Okay, now, 2 things I'll show real quick. If you're doing an IDF study and our rules for design storms, for designing projects, not for hydrologic risk analysis and not for calibration, but when you get to the design phase and you're designing, or even out of this study, if you're doing an inflow design study, at the end, you're applying that 1.07 atmospheric moisture factor to account for expected increase in atmospheric moisture over the next 50 years at an assumed 50-year design life of the project. That was from REPS, recommendation from our scientists and the contractors for the REP study. Then what we would do then is apply that as what we'd recommend doing if you've created a separate MET model for each storm and a separate simulation. Then you can just go in here, say you have a PMP IDF, go in here and select a precip ratio, and then that precip ratio can be 1.07. That scales all your REPS design storms up by 7%. Okay, so I'm not going to do that now because we wouldn't do that until the end, until after model calibration comparison to historic values of the observed flood record. And we also would not apply that if we're just doing a hydrologic risk assessment, because risk assessments generally assess present risk. They're not really forward looking in terms of population at risk or any other probability of failure or anything in the future. So hopefully that was clear on that. And then the only other tip here would be, once you get 25 storms, a handy thing is just to do this multiple compute, and then you can select all. So once I have this build out with 25 storms, I'm selecting all 25, hit compute, and instead of having to pick every one of them, it just runs all the storms, and then we'll get results. So last thing in this section 7 video tutorial, and let's wrap it up here, is QC checking. Obviously, there have been errors along the way that I've caught, but I incorrectly put in miles for reach lengths instead of feet so I corrected the reach lengths. I'd originally erroneously put in miles, corrected that to feet. Then we had this issue where I'd incorrectly used meters instead of extracted from GIS instead of feet. I had to correct that in our reach cross section. There's obviously a lot of data in this model at this point: rainfall data, control spec, loss parameters, Clarkian hydrograph parameters, reach routing. It needs to be quality control checked thoroughly. That can be done using the properties tables that we've printed out from section 5 of the guidelines, using the parameter summary table we had from section 6. Okay, so I find that an easy way to look at the model and check it is just to print the standard report, and that will be done after we compute, run the simulations and have data. Then we'll go to tools, reports, generate a standard report. It'll ask us where we save it, and then once we run it, it'll have options in here for what we want to model, what we want to print in our report, and that's just, it dumps all the parameters by sub-basin, methods, and it just ends up being an easy way to um, check the model inputs. You could have, I would just have this printed out and then have my table 6 parameter summary table and check those, make sure everything went in correctly. Check drainage areas. The precipitation data, I think, needs to be checked in the program. I don't know that you can dump that out, and it would be a lot of it. But the thing I would typically do there is have my output from the reps precip frequency, the precip frequency estimates from the Met portal, and then my PMP, basin average PMP output from the reps PMP evaluation tool, the GIS tool. And I would just go down through and check each one of these rainfall storms, probably just against the graph quickly, and make sure that I have the right rainfall in each of these precipitation gauges. And then I would go back and check the Met models probably one more time just to make sure they're all calling the correct precip gauges for the design storm, and have the partial area correct if that's applicable to the storm. Okay, so that's it. We're done with the model. That's section 7. And then in section 8 here, we'll go through model results, look at those standard reports again, and show what kind of reporting we want to see for a hydrology report that's going to be submitted for Colorado Dam Safety Review. Okay, thanks for your time on this, and hope it was helpful.